All right, gang, here we go. This is for Physics, Unit 5, Part 3. We're talking about the relationship between heat and work. Should be pretty easy-ish. All right. So, first of all, let's just start off talking about something. Imagine you have a small balloon, right? You take that balloon and you hold it in your hands and then you squeeze it into a smaller volume. Have you done work? Well, yeah, you've done work, right? Remember, based on the physics definition of work that we've used so far, work is equal to force times the displacement. Work equals force times distance. There's an angle part of it, but we don't really care about that, right? You've applied a force, and the outside of the balloon got condensed down, so you moved it a distance, right? So force times distance. So has heat been transferred in or out of the balloon? Well, if you think about it, you had to have added heat to your balloon because you applied force to it, and so those molecules are going to be moving in a much smaller space. So their temperature, their heat, or they have had heat. Remember, heat in the in the physics definition, heat is defined as the transfer of energy. Okay, transfer of energy. All right. And so, because you added energy to your system, you did work. Work is energy, right? And so, as you did work to it, you added energy. So, therefore, you had to have added heat to the system. So, the internal energy of the balloon also had to have changed, right? Because your internal energy, remember, is the combination of your kinetic and your potential energy, right? So by adding in your thing here, you've added in potential energy, right? Because you could almost imagine this balloon as being like an elastic situation, right? Remember with the spring, when you took a spring, you stretched it out, you had a potential energy, an elastic potential energy, and as you compressed your spring, you also had elastic potential energy because your spring wants to return to its normal, the regular size. Okay, and so you've got this potential elastic potential energy going on. Okay, and so this really highlights something very important that you need to start working on, especially in this unit. Is so far in physics we've talked a lot about a lot of different words and vocabulary words that people use all the time in real life, right? We use this stuff all the time in real life, but in the physics world, they mean slightly different things. Okay, and so we really have to be paying attention to, well, what exactly does that mean? Okay, and so in your head, when you're working through these things, I challenge you to really pay attention to making sure you're using the correct vocabulary words in the right way based on the physics definition. It'll go a long ways to help making sure you understand multiple choice questions and otherwise as you move along. All right. Let's see. So heat, work, and energy. So this is a great way of you making sure, I'm just of helping you understand, making sure that you understand the definitions of these things. So imagine you take a nail and you pull it from a piece of wood using a hammer, right? Your nail's stuck in there. You peel it up with a hammer. Did you do work? Well, yeah, you added a force and it moved a distance, right? That just makes sense. Now, since work is done, that means you had to have added energy, right? The energy of the nail must have increased. In what way is it increased in this specific example? Well, the nail is going to have friction against the wood, right? And friction is really just kinetic energy. And so, therefore, the temperature is going to go up. And because the kinetic energy went up, the internal energy also had to go up, right? And so that's kind of what we're saying in this line here. Now the nail is hotter once it's gone through because of friction, right? You've increased that internal energy. So what will happen to the internal energy if you just take that nail and you lay it on the table over the next few minutes? Well, the internal energy it's going to be at a higher temperature, right? Because it's warmer, okay, and it's going to transfer this heat to its surroundings, and so then reaching thermal equilibrium, and so the nail will cool down, right, and its heat will leave. Okay. In class, we took a flask, right, and we put some water in it. So we had like a hot plate, right? We had an Erlenmeyer flask, all right. So there's our Erlenmeyer flask. Yeah, you know it. And then we put a balloon on it, right? And so we started with balloon, and the balloon started out deflated. I don't know why I made it a dash line. It was a solid balloon. Okay, so there's our balloon. Okay, on our Erlenmeyer flask, and then we heated up the Erlenmeyer flask. So here we go again. I'm going to draw it again. I know. Can he do it? Almost not. Almost not. All right. And then over time, the Erlenmeyer flask. This really should be the same shape. I don't know what I was doing. Anyway, so the balloon filled up, right? Because of this hot water. And we described it. We learned in chemistry that as we add heat, the molecules move faster. And because as the molecules move faster, they're going to take up more space. And as they take up more space, they can either increase the pressure or increase the volume. Now, because the balloon is stretchable, it's going to keep the same pressure as the atmospheric pressure, and so you have this pressure, or an isobaric system where the pressure stays the same, okay, and so your volume increases, right? And so, but let's start thinking about these thermodynamic quantities that we've learned so far. So is heat transferred? Well, yeah, heat is transferred. The flame, or the hot plate, is hotter than the glass, right? This is at a higher temperature than the glass was and the water inside of it, so therefore the hot plate transfers its energy via heat to the water inside of it, right? And that makes sense. So how is the internal energy of the water affected? Well, it's affected in a couple of different ways. It's the kinetic energy goes up, right? Remember, temperature is a measure of the average kinetic energy. So as the temperature goes up, okay, the kinetic energy of those molecules increases, and that increases your internal energy. And then also remember that a phase change is a point at which you're changing potential energy, right? Your temperature doesn't change, but your potential energy does. Remember, we had, our graph thing, and we had, the temperature change here, and then we had a phase change that was level, and then we had a temperature change and the phase change that was level, right? And so in here, we had a potential energy change, right? And so that was our phase changes. Okay, so as it changes into a gas, the potential energy increases. So the water's internal energy actually increases two different ways. As the kinetic energy goes up, the temperature goes up, and then when it reaches the boiling point, the water probably started boiling, and then they're in the flask, it started turning into a gas, and so you get a potential energy increase as well. Okay, so was any work done? Yes, the work was done in several different ways in this case. The most important place was that as the steam expands, the balloon moved, right? It went from here and went out, and we expanded out this way. So the molecules applied a force and pushed the outside air out of the way, okay? And so it did work, all right? So heat and work are energy that are transferred into or out of a system. Now there's something that I want you to start thinking about here, okay? Whenever we talk about thermodynamics, you'll always hear people start talking about the system, right? The system versus the surroundings, all right? And this is something that 99.99% of people that I've heard talk about thermodynamics use this as their starting point. And then the trouble is that a lot of people don't go back to it. So I'm going to try to refer back to this idea of system versus surroundings as much as possible. Okay, but so the system is just whatever you're looking at. So in the case of our Erlenmeyer flask and the balloon, that was our system. The water inside the Erlenmeyer flask with the balloon sitting on top, that's our system. The surroundings is everything else, literally everything else. So us in the room, the table, the classroom, the universe, right? That is the surroundings. So and in thermodynamics, a lot of times measuring the absolute quantities of the system of how much thermodynamic either heat or work are inside our system is either hard or impossible to measure or not very useful to know, so we don't bother it. What we really care about is what's transferring across this barrier between our system and our surroundings. So really we only care about what's changing between the two. Okay, and so so let's just think about this for a second. So when we're heating up our flask with the water and the balloon, our surroundings, or the hot plate, was adding heat to our system, right? So this was our Q value, or not adding heat, it was adding energy in the form of heat. It was the energy transferred across the barrier from the surroundings to the system, and in return the system was doing work on the surroundings, right? So this was the work of the system on the surroundings. All right, and so that's essentially the main idea, is that both of these things are energy that are being transferred into or out of our system. Surroundings puts energy into the system, and the system puts energy back on the surroundings, and they just change forms, right? One of them was in the form of heat, and the other one was in the form of work. All right, and so that's essentially what happens. And then when we took the Erlenmeyer flask off the hot plate, we took it down. These were reversed. The system was transferring heat to the surroundings, and in reverse, the surroundings was doing work on the balloon. Right, the balloon was deflating. Okay, so we're going to have a new definition of work here. Okay, so far we know a couple other definitions or formulas for work. We knew work is equal to force times displacement. We also talked about how work is equal to the change in the kinetic energy. All right, here's another one. Now this work only does when it's a gas. Okay, work is equal to the pressure times the change in the volume, or the P. A lot of times you'll hear people refer to this as the PV work. All right, pressure volume work. Okay. Couple of definitions here. Work is positive if your delta V is positive. Okay, so if your volume is increasing, your work is going to be positive. All right, or essentially what we're saying is that expanding gases do work on their surroundings. The expanding gases do work. So this is our balloon getting bigger. The balloon was expanding, right? The gas was expanding, and so you end up with more work being done. All right, positive work. Work is negative if the volume decreases, right? Your volume is getting smaller. The surroundings are doing work on the gas, so we call that work negative. All right, and you'll actually see if you watch some other YouTube videos or read some other books, they might actually flip this definition of work being positive or negative. We're going to stick with this one based on what the textbook says. Work is positive if the gas is doing work on the surroundings. All right, so try to keep that straight. If you go hunting around, get a wild hair, and you start researching a bunch, just make sure you pay attention to that idea. All right. Now, to wrap it up here, we're going to talk about 3 different thermodynamic processes you need to be familiar with. All right, and in my opinion, these can be kind of tricky to try to keep straight. So you got to really practice trying to apply these processes to different cases. All right, so isovolumetric processes. Now, whenever you see the word iso means the same or equal. All right. So same, and then volumetric, you should say there. Well, that just means volume. So really what we're saying is this is a process in which volume, okay, is constant. All right, that's really what we're saying here. Volume is constant. All right. Now, if volume is constant, then that means the work has to be equal to 0, because we just learned that work in a gas is equal to pressure times volume, right? And if our volume is equal to 0, that means our work also has to be 0. So if you have an isovolumetric process, your system cannot do physics work. Okay, it cannot move something, right? Because your volume's not changing. Okay, now the internal energy can change, right? Because you can have kinetic and potential energy changes. Okay, and you may also have heat being exchanged, your energy being transferred. All right, so bomb calorimeter is like the quintessential example of an isovolumetric process that's actually useful. Okay, we use bomb calorimeters to establish heats of reactions. Okay, so you take some sort of combustible material, put it in here, it's called the bomb, right? And then put that in there with a lid that lets oxygen in. Okay, and then some sort of electrode to give it that spark to blow it up. You put it in water, and essentially what you do is you blow up this guy, measure how much the water temperature increased, and then you can figure out how much energy it produced. All right, so this is essentially exactly what we did in our heat capacity lab, only instead of taking something hot, you started with something that was cool and then blew it up, so it's kind of fun. But the volume in here does not change, right? It's sealed, and so therefore you can assume that no work was being done, so the only energy produced was into the water, that's kind of the idea. All right, next one is isothermal process. Okay, isothermal processes occur when there's no change in temperature. Remember, iso means same, thermal means temperature. Okay, so no change in temperature. So because there's no change in temperature, your change in your internal energy has to be equal to 0. Now, work can be done in an isothermal process, and heat may be exchanged. Okay, so I want you to imagine that you found a magic mountain. Okay, you found a magic mountain, right? Here's your mountain. Now, this magic mountain is special because so pressure is higher here. We have higher pressure and lower pressure, right? So that's normal mountain behavior. However, this mountain is special because the temperature is the same at the bottom as it is at the top. So here, your temperature 1 is equal to temperature 2. So this is the same temperature at the bottom and at the top. All right. So if you take a balloon, you fill it up, you're at the bottom of this mountain. Okay, and then you walk yourself up to the top of this mountain. Your balloon is going to expand, right? Because it's a lower pressure on top of your mountain, and so your balloon is going to expand because it has to equalize that pressure. But as it expands, your gas is going to automatically start to cool because it's doing work on the surroundings, right? But as it does work, because the temperature is the same outside, the temperature, you've got this giant source of energy, the entire mountain's worth of energy, in order to warm back up those molecules. And because you're walking up a mountain, you're going freaking slow. Okay, I don't know if you guys have ever climbed a mountain, but it takes a lot of energy. So anyway, so you're climbing this mountain, you're going up this, and your energy is coming from the outside going into your balloon. Okay, and so the temperature remains the same, but your balloon is still able to do work on the outside. So the internal energy of the balloon hasn't changed, but you still have had work being done and energy being exchanged. All right, last one here is an adiabatic process. In an adiabatic process, no heat is transferred, so your Q equals 0. Now, as this happens, that means your internal energy may change, okay? All right, your internal energy can change because you can still have this change in temperature, and you may also still be doing work. Okay. Now the thing with adiabatic processes is most real-world examples have to be taking place in very rapid processes. Okay. If you've ever used a can of air, right? You spray that can of air, you use it to dust your computer or whatever keyboard. If you spray that thing for like 10 or 15 seconds, you'll feel that can start to get very cool, right? And that's because your can is producing work, right? It's doing work on the surroundings, but no heat is being exchanged. So you create a temperature differential of what's inside the can versus what's outside the can. And so then you feel it get cold because it's literally stealing heat from your hand. Okay, and so another example of this is essentially the same idea. You have a tank of helium and a balloon, and you're filling up a balloon. Now a helium tank is at a very, very high pressure, and so when it fills up the balloon is doing work on the surroundings. Your system is doing work on your surroundings, and so therefore it expands, and you'll actually have your tank will actually get cooler. Now, if you have a giant tank of helium, like your temperature change is going to be very, very minimal unless you're filling up a ton of balloons very, very fast. But regardless, because your tank is well insulated, you're not going to have very much heat exchanged. All right, and so that's essentially the idea of your three thermodynamic processes. They're kind of tricky. I really recommend, we'll do some more practice in class, but I really recommend walking them through. It's not enough just to do note cards to understand, although those would help in understanding those three processes, when work is held constant, when, what happens to your internal energy, what happens to your heat, okay? But also, like, try to think through different processes and what would occur, which system is it, what happens to your internal energy, your work, and your heat as you change each of those three things. So do lots of practice problems. It's really important to kind of have a good handle on this as we move forward into the laws of thermodynamics. It'll go a long ways to helping you out. All right, do your practice. Let me know if you have any questions, and I'll see you on the flip side.